The Fermi Gamma Ray Space Telescope is a powerful space observatory that opens a wide window on the universe. Gamma rays are the highest energy form of light, and the gamma ray sky is spectacularly different from the one we perceive with our own eyes. With a huge leap in all key capabilities, Fermi is enabling scientists to observe some of the universe's most powerful phenomena, including supermassive black holes, pulsars, and gamma ray bursts, which briefly outshine whole galaxies.
Gamma rays are the highest energy form of light.
There's the light we see with our eyes, but there are lots of other types of light. Gamma rays are the most energetic form of light, the most powerful.
Gamma rays are the part of what we call the electromagnetic spectrum, which starts in radio at very long wavelengths, goes through optical, then through X-rays, and then gamma rays are the very highest energy form of that type of radiation.
The reason that it's important to look at the high-energy gamma rays is that many objects, the most violent and some of the most interesting objects in the universe, emit most of their light in this high-energy gamma ray part.
And the only thing that can generate gamma rays are incredibly violent events, incredibly energetic events. And we're talking stars exploding and neutron stars with really strong magnetic fields and really exotic and strange objects like that.
It's like a Christmas tree. It's shining and it's flaring and there are eruptions every day.
Gamma ray bursts being an example, something that for a brief instant of time outshines the entire rest of the universe.
These are the biggest explosions in the universe.
Fermi has two instruments for observing gamma rays. Its Large Area Telescope, or LAT, maps gamma rays over the entire sky every 3 hours and is Fermi's main detector. The other instrument is called the Gamma Ray Burst Monitor, or GBM. It looks for spectacular flashes of gamma rays from, among other things, the birth of black holes far across the universe. Hidden deep within a group of ancient stars, there lurks a young and powerful enigma. This is NGC 6624, a globular cluster near our galaxy's center thought to be about 10 billion years old. NASA's Fermi Gamma Ray Space Telescope detects high-energy radiation from many globular clusters. Usually what Fermi is seeing is the cumulative gamma rays from all of the old pulsars in these clusters. A pulsar is a rapidly spinning neutron star, which is the small, incredibly dense remnant of a much more massive star. A teaspoon of matter from a neutron star weighs as much as Mount Everest, and a neutron star is so compact that a ball about 15 miles across contains more matter than our sun. Neutron stars spin between 7 and 40,000 times a minute and form with incredibly strong magnetic fields. Rapid spin and intense magnetic fields drive powerful beams of electromagnetic radiation, including gamma rays. As the pulsar rotates, these beams sweep the sky like a lighthouse. To a distant observer, the pulsar appears to blink on and off. Pulsars slow down as they age, but some of the oldest pulsars spin hundreds of times a second. Each of these millisecond pulsars orbits a normal star. Over time, the impact of gas pulled from the normal star has spun the pulsar up to incredible speeds. This accretion may be the cause of their weaker magnetic fields. Despite this, these pulsars also emit gamma rays. But the millisecond pulsar in NGC 6624 doesn't fit neatly into this picture. It's so bright that Fermi directly detects its gamma rays, and so far it's the only one seen in a globular cluster with such power. It's losing energy so fast that it must be only around 25 million years old, the youngest millisecond pulsar ever found. It also possesses the strongest magnetic field yet observed in a millisecond pulsar. Its high energy output dooms it to fade out quickly on astronomical timescales, and scientists wonder if this object represents a new way to make millisecond pulsars. In 3 years, Fermi has detected more than 100 gamma ray pulsars, shown here using animated pulses 50 times slower than actual speed. Recent advances in data analysis helped Fermi reach this milestone, and these techniques promise to find many more gamma ray pulsars. Some of these are historical, the first gamma ray pulsars ever discovered. Others, like the pulsar in NGC 6624, were first seen by radio telescopes and then observed by Fermi. Some were first spotted in radio after investigating unknown sources detected by Fermi, and about a third of gamma ray pulsars were discovered by Fermi on the basis of their gamma ray pulsations alone. Fermi's gamma ray observations are literally showing us these incredible stellar lighthouses in a new light. The Crab Nebula is one of the brightest sources of high-energy radiation in the sky. Little wonder, it's the expanding remains of an exploded star, a supernova seen in the year 1054. Recently, astronomers using satellites sensitive to the highest energy form of light, gamma rays, have observed incredible flares in the nebula that theorists are hard-pressed to explain. The supernova left behind a magnetized neutron star, a pulsar. It's about the size of Washington, D.C., but it spins 30 times a second. Each rotation sweeps a lighthouse-like beam past us, creating a pulse of electromagnetic energy detectable across the spectrum. The pulsar in the Crab Nebula is among the brightest sources. As the pulsar spins, its powerful magnetic field causes particles to flow. These currents ultimately light up the nebula. But as bright as the pulsar is in gamma rays, it isn't the source of the flares. NASA's Fermi Gamma Ray Space Telescope can look in between the pulsar's brilliant pulses to reveal the faint gamma rays from the underlying nebula. Yet several times since 2009, enormous flares have erupted somewhere within the nebula. The most powerful one to date lasted 6 days and made the nebula 30 times brighter than normal and 5 times brighter than previous flares. During the huge flare, astronomers also studied the crab with NASA's Chandra X-ray Observatory. Chandra's keen X-ray eye saw lots of activity, but none of it seems correlated to the superflare. This hints that whatever's causing the flare is happening within about a third of a light year from the pulsar. And rapid changes in the rise and fall of gamma rays imply that the emission region is very small, comparable in size to our solar system. Scientists say the gamma rays most likely arise from electrons moving near the speed of light, which emit gamma rays as they interact with magnetic fields. But to account for these flares, the electrons must have the highest energies ever seen in cosmic sources, 100 times higher than can be achieved in the most powerful particle accelerators on Earth. Even after 1,000 years, the heart of this shattered star still offers scientists glimpses of staggering energies and cutting-edge science.